Andy is a professor from Imperial College in London, and he's very well known for many of his seminal works on visual SLAM and spatial AI. So today he's going to give a presentation on spatial AI. Let's welcome Andy.
Thank you very much. Yeah, so I've called my talk today Representations for Spatial AI, and I'll explain what I mean by that. So thank you very much for inviting me. So yes, I've been working on Visual SLAM for a lot of years, and this has been about estimating the motion of robots in scenes and building maps of scenes. And this has been really cool for me, who's worked on this for a long time, to see that there are now products you can actually buy that do Visual SLAM, and they're in several areas like home robots, smartphones, headsets, and also drones. But if we think about what these projects actually do so far, it's mainly about sparse mapping, some amount of dense mapping, some amount of semantic understanding. But I think it would be true to say that these are relatively early products so far. So I've always been interested in where this technology is going in the longer term, and I have a vision that SLAM is evolving into something bigger and more general that I call spatial AI, and it's this general spatial intelligence that we think intelligent systems need to operate in an embodied way in the real world. And I hope you can already see the link to what a lot of you are interested in this workshop. So where might that take us in the longer term? I think to much more ambitious type of products. So this is just a kind of mocked up image that I found somewhere on the internet, but let's think about things like general purpose home robots. Let's think about really powerful augmented reality systems that you could wear all day, that would remember everything you do and see. And that would also operate within the constraints of real products like low weight and long battery life. So those are the kind of things that we're really aiming for. And I would argue strongly that we're only at the kind of beginning of research in this area. There's so much more to do. There's a gap to cross. There's the things that we can currently buy. There's research prototypes in labs such as mine and many around the world, and in companies. And there's where we really need to get to. And I think we need orders of magnitude of improvement yet, both in performance, but also fitting that performance into the constraints of real products. So I've been very interested in this issue in general. How are we going to get there? I've got some discussion papers which you might be interested in looking at to find out more about my thinking here. They're called future mapping. There's 2 of them so far. So some of the hypotheses I make in those papers include that I think there's a general sort of structure and set of capabilities that a spatial AI system needs, which are relatively independent of the particular application. So whether it's a drone or a vacuum cleaner robot or an AR system, I think that a useful spatial AI system should build a persistent and understandable scene representation, which is somewhat close to metric 3D geometry, at least locally. So of course, there'll be many different parameters that differ between different applications, but I think there'll be something in common in terms of the sort of representation that they build of the scene. So I'll mention this paper. I know that there are several other co-authors of this paper who are involved in this workshop. So this was a fantastic thing that I was involved in last year, really. During the lockdown, we had many regular meetings to talk about this. But thinking about what are the sort of really challenging things that we could do in spatial AI or embodied AI over the longer term, and trying to really push research by defining harder challenges. And we came up with this rather general idea of rearrangement as a way of specifying a task that encompasses very many things. And what we really did in this paper were to talk about things like how would you specify a rearrangement task, and then how would you evaluate performance. And I guess in the context of all the work I've been doing in spatial AI, I'm particularly interested in these sort of complex tasks. So a rearrangement task might be, tidying up a kitchen or something like that, because in my mind, they really motivate work on representation and kind of long-term scene understanding to make persistent compositional scene representations which can actually be updated by an agent. So that's really my interest in that I hope it will drive research towards the sort of spatial AI capabilities that I think will ultimately enable these kind of products I'm interested in the long term. So just to mention, so within that rearrangement paper, we feature and talk about several existing simulated workbenches which are available for people to experiment with these sort of rearrangement tasks. And there's one of those that's come out of our lab at Imperial College called RL Bench, led by Stephen James. And this is a really nice robot simulation environment with many unique hand-designed tasks that you can experiment with. And that's all available open source. So going back to kind of my main theme of spatial AI and representation. So we've been through various stages of SLAM systems and spatial AI systems that can build better representations in real time. So going back to the early days of Visual SLAM, what we could do was build very sparse feature point representations of scenes, which were good enough to track the position of a camera, but didn't really give us much information about the scene. The next level up was dense SLAM. So this is an example called Elastic Fusion from our lab. So this is a system which using real-time processing, a depth camera, we could build this sort of highly detailed geometric model of a scene in real time. But this is still basically geometry. So the next level, and what I think is very much an area of current research, is how do we get semantic meaning into representations like this? And one of our first attempts in that area was a system called Semantic Fusion, which is more or less, build a dense reconstruction, use a CNN which runs on keyframes and gives us semantic labels per pixel, and project those labels onto the 3D scene and fuse them to try and get a 3D labeled scene. So that worked, somewhat well, I would say. It worked well in some scenes, not so well in others. But the other thing to point out about that system is it was really just quite a heavyweight system. So this is just a rough kind of system module level diagram of semantic fusion, showing all the different blocks of computation, all the different types of data that were involved. This system ran on a CPU and GPU system and was moving, many megabytes of data around. So from several points of view, I think this is, not satisfactory yet. So it doesn't yet achieve the results that we need, but also it's too heavyweight to ever think of pushing down onto tiny embedded hardware. So how are we really going to attack that? So I would say there's two main lines of research that I'm interested in. So the one I'm going to focus on today is representation. So how do we, for instance, think about some of these lines in this graph here represent moving many megabytes of data around, which represent things like a 3D map of the scene, which might be represented by, a volumetric grid or a mesh of millions of vertices or something like that. Those don't seem like the right kind of things to be doing if we want these systems to ever be efficient. The second line of attack is around hardware, and in particular, new sorts of sensing and processing hardware, but I'm not going to have the chance to talk about that today. So just to really focus on representation, so of course, the tool that's really come into SLAM over the last few years, which has enabled us in particular to do new things in representation, is deep learning. So deep learning is a way of automatically trying to find these kind of efficient ways of describing complicated data, and that's really useful to us. Now, clearly, there's people who are very interested in end-to-end learned systems. I've come from the kind of starting point of fully hand-designed algorithms. What I'd just like to point out is there's a massive, almost continuous space in between these two endpoints. And I think what nearly all of us are doing in SLAM and spatial AI at the moment is somewhere in the middle here. We're building modular systems that have some learned components and some human designed components. And I just think there's so much space to operate here. So I'll show you some of the things that we've been doing, which I think usually fit somewhere in between here. So some kind of learning and some kind of hand-designed, usually geometrical, probabilistic type of reasoning, which go back to our, old SLAM and geometry background. We've looked at ways that neural networks can help us to basically compress our representations of scenes. So we had a series of papers called Code SLAM and then Scene Code, and don't worry too much about the details of this network, but the basic idea is that if you take many images, both with color and depth of typical scenes, so these would normally be indoor scenes, then of course, an image has hundreds of thousands of pixels, and in principle, an image is hundreds of thousands of dimensional space, but actually the variation in real world images is much lower than that. So there are methods that can go from a single image to predicting depth or to predicting semantics, and we can use those. But what we do in the Code SLAM method is also learn a low dimensional embedding for the ways that those depth or semantic images will tend to vary among our data set. So what that allows us to build is a SLAM system where we build a map of keyframes, and associated with that keyframe is a low dimensional code, which then relates to the neural network that we've got to define a fairly low dimensional representation of the scene depth and the scene semantics at that position. And because it's low dimensional, we can then jointly optimize that across multiple views and apply our kind of normal SLAM tricks. So if you're interested in that sort of method, I would recommend looking at this paper, Deep Factors, where we have open source code available where you can actually experiment with these methods. So another method to mention, which is about using neural networks to represent whole scenes, is one that we've just made public very recently called IMAP. So this is a system, it's in some ways closely related to papers like NERF that use an implicit neural network as a fully connected MLP network to represent a scene. What we show in IMAP for the first time is that you can actually train a network like that in real time. So here's a quick demo. So we've got a handheld depth camera, which we're moving around in this room. It's capturing a sequence of RGB and depth frames. And then in real time, it's trying to train a fairly small neural network using this implicit form, such that when we raycast into this implicit network, we can generate RGB and depth frames, and then we optimize the parameters of the network such that these renderings match up with the actual images that we have captured. And remarkably, within just a few minutes of real-time operation, and we can actually optimize this network into a quite accurate representation of the scene. So you'll see it's still kind of early days at the moment. It starts out with this relatively sort of blobby, low resolution looking reconstruction, but as the camera explores more and more and looks at different parts of the scene, you'll see that it gradually gets sharper, and it actually has some really nice properties, like it will always generate a fully continuous surface such that it will do things like complete the back of objects, even when we've never seen the back of this object, which is a ball on the floor. But the network, just because of the internal structure of this network, it fills it in quite a compelling way. And just to stress, this is a network which is just trained from scratch in this one scene. It's never seen any prior data before. So the only priors that we bring to bear here are what's implicit in the structure of the network that we use. So let me just let this run to the end. So we've pretty much finished exploring the room here. We're looking close up at some objects and filling in a few more details, like these items on the shelf over here. And here we just see a view of the final kind of 3D reconstruction of the room. So this is quite interesting, in particular because this is quite a small neural network. There's only about a megabyte of weights involved in this neural network. And in fact, it's done a really nice job of compressing all of this detail into the scene, into that relatively small representation. And so that's very much in line with what we're interested in. So the other kind of main line of work is building representations of scenes that focus much more on the objects in the scene. So this goes back to the first paper we did in this direction, was one called SLAM++ in about 2013, where we were able to recognize objects in the scene and build a SLAM map that really just consisted at the level of objects. So each of these objects was recognized and then serves as like a landmark in our SLAM map. So this is again, a very, very efficient representation of the scene. Sorry, I think I will move on and show you some of the latest developments in this direction. So one paper we published last year was called More Fusion, which is about using a representation like that, where here we're assuming that we come to a scene with prior knowledge of precisely some of the objects that are going to be present. So we look at this scene and we actually have CAD models available of these particular objects that we know are likely to be present. But then we solve the rather difficult problem of inferring their positions in the case where they're all kind of lying on top of each other, there's clutter and so on. So we're jointly reasoning volumetrically about the position and shape of all of these objects. And you'll see that eventually, after scanning around for a little bit from a camera that's mounted on the robot arm here, we're able to accurately fit their positions. And we do that accurately enough that then we can then, do some robot action. So here now we have a grasping procedure where we need to clear some of the objects away such that we're able to then grasp an object of interest. And because we've got proper 3D reasoning going on here, we're not just picking up objects and dropping them necessarily. We can actually pick up objects and in the end precisely place them if we want to. And I'm just going to finish, show you this one. So I think the latest work we've done in this area of object-based representation is a system called NodeSLAM. So this is slightly weaker than the last system in that we don't assume we have precise prior CAD models of all the objects we're going to see in the scene. We assume we have category level shape models. So we have from databases of objects. So for instance, we've got 1,000 3D mugs in our database. And from that, we've learned a shape space model of mugs using a neural network, which then at runtime, as we capture images from a moving camera, we detect objects, we recognize their class, we pull in the appropriate category level shape model, and we optimize its shape to fit what we see. So again, we're building a model of the scene, which really consists of a map of objects. That really is what the map is. It's not like there's another map and then there's objects on top. The objects are the map. So that's a really, really efficient representation. It can be jointly optimized. We can do loop closure and all those SLAM things. And then here we show how we can then use that for manipulation. So we scan this scene, we detect objects, we fit the shape models, and then we've recognized and fit these objects accurately enough that then we can do very, very precise manipulation. So here what we're going to do is now pick up the 4 bowls in order and place them very precisely into a stack in this box here. So you can understand how this requires, very, very precise knowledge of the shape and the poses of these objects in order to do that. And it's this kind of representation that's enabled us to do that. Okay, I'm going to finish and conclude there. So yeah, spatial AI research is what I'm interested in. I think it's a long-term research program that we're going to be doing for a long time yet, and there's plenty of interesting challenges. And just to quickly mention my affiliations, so I lead the Davison Robotics Lab at Imperial College, which is an academic lab working in collaboration with Dyson, in particular with interests in home robotics. And I'm also co-founder of SlamCore, which is a London-based startup building applied spatial AI solutions. So thanks very much.
Thank you, Andy, for the very nice talk. We have time for one or two quick questions. If you have a question, you might just type it directly on the chat. I will begin with a question. Andy, you mentioned the representation for the SNAM problem. It's a very interesting point, but what do you think about the optimization methods? In recent years, the learning to optimize methods applied to SNAMs and also to say optical flow last year, the raft paper. So what do you think about this learning to optimization? Will they someday replace the traditional Liebenberg marker kind of thing?
Yeah, I know about some of that work, and I do think it's interesting. So clearly, if you're solving an optimization problem that has a similar structure to many that you've seen in the past, then I do believe that learning could help, because the optimization problems that we have in SLAM are often very complex. They're these huge sort of sparse graph type problems that we have to optimize. And yeah, sure, I'm interested in that. Yeah.
Yeah. Great. Do we have other questions?